Hello, everybody, and welcome back to Why Slice. Let's talk about applications of computing. And I'm going to give you my personal perspective on this. I'm a computer science researcher, so a lot of what I do, actually, most of what I do, really involves computer science. But I want to talk about an example where we are applying computer science concepts to other domains. In particular, the work that we're doing at the Artificially Intelligent Manufacturing Center at the University of Wyoming, which involves people from computer science, people from mechanical engineering, and chemical engineering as well. And I want to give you a little bit of an idea of the computer science concepts that we are applying in these other application domains. In particular, the way that we're applying this that allows us to apply the same computer science concepts in different application domains with really only very minor modifications. So essentially what I want to talk about is the power of abstraction, which is very prominent in computer science. We have already talked about this a little bit in the previous video where I told you that you can use, for example, Zoom or the video conferencing software of your choice, regardless of the underlying network. It doesn't matter whether you have Wi-Fi, whether you're plugged in, whether you're at work, whether you're at home, in a coffee shop, you can use the same software. Same idea here, except that we're doing this in a research domain. Let's first talk about the application in chemical engineering. And this is something very exciting for me because it involves things that we can actually physically touch. And in a lot of computer science, certainly in my research, this is not usually the case. We have programs and we have things that we do on computers, but there's nothing physical, nothing that we can play around with. Okay, so what is this application? Well, we're interested in producing graphene, which is this wonder material that you may have heard about. Great strength, it conducts electricity, it conducts heat, and really only consists of a single layer of carbon atoms that are arranged in a hexagonal grid. As it turns out, manufacturing this in practice is actually quite difficult, and that's the reason why you haven't really seen this taken over everything that we've been doing. So that's one of the problems that we consider in our research center. In particular, we take a precursor material that we can produce relatively easily, graphene oxide, and then we irradiate it with a laser to produce graphene. So we have a dark coal looking material, and then we shine a laser onto it. We burn it essentially, and thus transform it into graphene. Lots of different applications for this. For example, flexible and very small circuits, because the graphene oxide that we start with is not electrically conductive, but the lines of graphene that we can create using a laser are. So, great material with lots of potential. What are we actually doing there, and how are we applying computer science? Well, it turns out that this irradiation process is actually somewhat difficult because, for example, if we apply too much power to the laser, then we simply burn a hole in the material and we don't affect the transformation to graphene that we're really interested in. Similarly, if we're not applying it long enough or with not enough power, nothing happens, and again, we don't end up with the graphene that we're interested in. In an ideal world, we would, of course, understand the processes that govern this transformation from graphene oxide into graphene well enough that we could simply say, well, this is the power that you need to apply, and this is the how long you should apply this power for. But in practice, unfortunately, we don't, at least at the moment, have this knowledge. Therefore, we're using computer science concepts, in particular concepts from artificial intelligence and machine learning, to intelligently explore this parameter space, the different things that we can do to effect this transformation, the power we apply to the laser, the duration we apply it to a particular spot, or if we're moving it to create a line, the speed at which we're moving it, and a bunch of additional experimental parameter that we can change when we're doing this in practice. How do we do this? Well, turns out that a good way of doing this is something that is intuitively very similar to what we would do as a human. We first run a bunch of different experiments. We evaluate different settings for power and different settings for duration and these things like that. And we simply see what works well. And then we do more things like the things that work well. We want to stay away from the stuff that didn't work because, well, we're really not interested in making it not work. We want to make it work. The advantage of having a computer do this instead of a human is that we humans are really not very good at processing large amounts of data. If you're talking about a very small number of data points, then yes, okay, we can definitely deal with that. Once we start talking about a couple of dozen or a couple of hundreds or more than that, then it becomes really, really difficult for humans to hold all of that information in our heads at the same time and make good decisions based on that. Computers don't really have that problem. The more information you give them, the better the decisions become, in fact, because more knowledge can be derived from it, and our data analysis methods become more powerful because they have more data to go on. And that's really the idea here. We're applying concepts from computer science, which, as I've talked before, computer science to me is something inherently multidisciplinary. So in this case, this really involves concepts from mostly statistics as well as a lot of things in artificial intelligence and especially machine learning. We apply these to this particular domain in chemical engineering, this particular problem, and we're able to achieve better results through the application than we can achieve by not applying computing, by having humans do the same thing instead. We are applying the same kind of techniques and the same computer science concepts in other application domains as well. In particular, we have another example, another problem, this time in mechanical engineering, different application domain. Here we want to create new materials. In particular, we want to create new materials with a higher energy absorption. Think, for example, the bumper on your car. When you hit something or something hits you, you want the bumper to absorb as much of that energy as possible because that means that you inside the car are going to be safer. Less of that energy of the impact is going to reach you. Completely different problem, very similar from a computer science perspective though, because in this case, it also turns out that we have parameters that we can set to achieve particular materials, and we want to optimize over this space. We want to find a material, a parameter setting that produces a material with the desired properties that we want for this particular application. And it turns out that in this particular case, we're even applying the same algorithm and the same code, the same implementation, very different problems, same code that we can apply with very minor modifications for the application domain. And this is, for me, as I said before, one of the powers and one of the really cool things about computer science, because we're developing algorithms, we're developing approaches, we're developing methods that can be applied to many different applications with only minor modifications. Another example of this that you might be more familiar with are data analysis tools that we have talked about before. If you think of Excel, you can do all kinds of different data analysis with this. You don't need a separate program to analyze this particular type of data. And then you're using a different program to produce a graph for that, and yet another program to read it in. You can do all of that in one program. It's a general purpose thing, and this is really where a lot of the power of computer science comes from. General purpose things, general purpose algorithms, implementations, approaches that can be applied in many different application domains.